Okay, so for this next video, I'm going to be diving into deriving the finite differencing equation and then actually going ahead and graphing it, showing how the heat diffusion will occur for a bar in one direction. So before I start actually diving into how we're going to derive the finite differencing equation, I'm going to state some assumptions that we're going to use when working with this equation. The first assumption being there's no heat generation. So if you remember from the previous video, our volumetric heat generation term is going to be equal to 0. Another assumption is that heat diffuses only in one direction. So you have something that's infinitesimally small, or it'll only travel in one plane, and that will be stated as your heat diffusion. Your second differential with respect to y, the change in time of temperature, and your change in temperature as a second differential with respect to the z-axis will both be 0. So that simplifies two of our terms from the previous equation, where we derived the heat diffusion equation for Cartesian coordinates. Another thing I'm just going to briefly touch upon, this is the heat diffusivity constant, and that's just going to be equal to your thermal conductivity times your, it's going to be equal to, yes, your thermal conductivity over your density and your specific heat capacity for that whatever material you're using. And we'll go ahead and describe the scenario that we're going to be working with. So we're going to be working with a bar of finite length with initial length 0, initial position 0, and at this, the temperature at J, which I'm going to be using to reference position, J is going to be equal to 0. At any time, this left-hand side of the bar is going to be equal to 350 degrees Kelvin. On the right-hand side of the bar, we don't know, let's just call it L. We don't know the set length for this. We'll be saying the temperature of this bar is also connected to something that has a constant temperature. And that's going to be 400 degrees Kelvin. At any time, for time, let me just write this blanket statement of your time in between 0 to infinity. These two statements will be true. And another component is initially the bar is at rest with temperature of 300 degrees Kelvin. So let me write over here, initial conditions. Those initial conditions are at any J value. So that's at any position along the bar. Temperature is equal to 300 degrees Kelvin at time is equal to 0. So that's your initial condition there. So any segment along the bar, temperature is going to be 300 degrees Kelvin initially. So finite differencing revolves basically around this theory that you can take this bar only existing in one plane and segment it up into little chunks and little blocks. So you take this bar and you segment it into evenly dispersed blocks of width, that's a bad sign, of width delta x. And it's evenly distributed. You can chop it up as finely as you want, and we'll actually go ahead and, just for this case scenario, I don't know how many that is, might be 10, but it's abstract for what we're actually going to be doing and manipulating the equation. Next, we're going to actually look at the remaining heat diffusion equation for Cartesian coordinates and sort of breaking it down. So we have a change in temperature with respect to change in time, and essentially what that is saying is your temperature at any position J at a future time. So I'm going to be denotating time and position. Actually, I'll include this over in the right-hand side. Your temperature, J, is going to be your position, and N is going to be your time, where J j is equal to some integer times delta x. So it's a whole number times those little blocks. So you're not going to be dealing with in the middle of the block. You're assuming everything's uniform within that block. And for time, you're going to be again assuming it's n is equal to, well, I guess I shouldn't be using n. Those don't have any relations. Just, let's say a whole number, I'll call it a constant k. And then for time, it's going to be equal to, let's say another constant, let's just call it c. C sounds fun. C is the number of time steps in the future you are, and those are going to be by this set chunk of time. We're going to call that delta t. So in order to break up this term here, which is your temperature at a future time, your change in temperature with respect to change in time, you're going to have your temperature at your current position with one step forward into the future. So it's going to be n plus 1. And that's going to be minus your temperature, your previous temperature at that position. So it's going to be temperature T Jn, call that, that's how we denotate it. And then your change in time, we're just going to call that delta T. Moving on, we'll look at this term here. I'll actually pull it out, this second derivative, and sort of break it up and expand it further. And so it's a change in position of your change in temperature with respect to position. And essentially, this term equates to something over delta x. And this, we can apply the same sort of logic and thinking where we have our temperature at a position, and it's going to be one position forward. We're going to take the average of those two. So this change in temperature with respect to position, we're going to say that is equal to, actually flip over here, your temperature at the same, here, let's call it this, your temperature at that same position, or at a future position, so it's because it's your average, so it's your temperature at that position, one in front of what you're working with. We're going to have time constant, so it's going to be the same time, minus your temperature at the position of interest at the same time interval. And that's all going to be over the delta x. And now, this is just for that inside term where we're going to be you're changing position with respect to x, and we must apply it again because it's also another change, so with respect to x. So you're going to have a second term that's going to correspond to your j position behind you. Actually, no, that's wrong. It's going to be another change is going to be your temperature at your current position at the same time minus your temperature at the previous position. So you're taking one block backwards and you're doing j minus 1 over delta x. And we have these two terms, and then we're going to be taking an average of them to substitute in for this term, second derivative of change in temperature with respect to position. So let's pull that over to the side. We still have our heat diffusivity term that remains untouched for now. And then inside, you're going to have, I hope my marker isn't dying on me, you're going to have your first term, which is going to be T j plus 1 at, well, so your temperature at your position one in front of what you're interested in at that same time, minus the position you're interested in, the temperature at what you're working with, over that change in position. And then you're going to be, to take a difference of the two, you're going to be subtracting the previous, so it's going to be minus that temperature at that position of interest, subtracting, we'll throw parentheses around it. It's going to be subtracting from your position, the temperature at your position one before it at the same time, and that's going to be over delta x also, because it's going to be an average. And then in order to take an average of both of these, we're going to divide it again by your position, your change in position, and that change in block. Okay, so we can simplify this a little bit going forward. And I'm actually going, I won't take too many steps. I'll move this over also. So yeah, I'm going to take a little steps, but I'll walk you through it and as I'm writing it out. So left-hand side, what's interesting, well, it's all interesting. What's interesting over here actually is your temperature at your position of interest one step in the future minus your temperature position of interest at your current temperature at the current time equal to your delta T times your heat of diffusivity. So we're moving this over and you can see here the denominators are the same, so we can condense this and also pull out an x squared. So we're going to x squared, and that's going to be your change in position squared. So the difference in that block squared. And then all within the parentheses, let's simplify it. We have your temperature at position 1 in front of what you're dealing with at the same time minus 2 times your temperature of your current position at the time of interest plus your temperature at position 1 behind times at that time of interest. And there you have that equation there. And we're going to do another trick to simplify it, and we're going to move over this time of initial position, which is what we know. We're going to move that over, and we'll actually be arriving at our final equation. So, just as restate again, the left-hand side of the equation is going to be your your temperature at one time interval into the future at your position of interest, and it's going to be equal to, it depends on your current temperature at that position, at that current point in time, plus, and this is where I'm actually going to group all these terms here together and call it a constant R, but I'll just read it out again. So where R, it relates to your change in time step, your heat diffusivity, which is going to be locked for your material, and your change in position. So when you're sort of manipulating this equation and determining this R value, what you have to play around with is the time interval you're looking at, along with the size of your blocks and how you are actually segmenting this bar you're dealing with. So that R is going to be multiplied to the temperature of the block 1 in front at that current time minus 2 times the temperature of your position of interest at that current time plus the temperature of the block 1 before it at that time of interest. And here you have your final equation of interest. And let's actually take a step back and look at this and sort of assess it analytically and see if this makes sense for what we're dealing with. So we have a position of interest, call it TJN. That block of interest at a time we know, and we know its temperature at that time N, and we want to go one step into the future. So we want to know what it is, what the temperature of that block J is one step into the future. So naturally, it's going to depend on what the temperature previously was. So we have that term here. That makes sense. It's going to be multiplied by some constant, which also relates to heat diffusivity of the material. So how heat and energy transfers through that material. And it's also going to depend on the block 1 in front of it. So this is your TJ plus 1 at that time. And it's also going to depend on the temperature of the block behind it. So TJ minus 1 at that same time. And that's pretty cool because you can see that for this block, it doesn't depend on 2 blocks in front of it or 2 blocks behind it or any number of blocks in front or behind. It only depends on its neighbors. And that makes sense because heat is only transferring through conduction in this instance. And this is the finite differencing equation for a linear bar. And I think that is all I'm going to cover in this video. I'm going to actually jump over to Google Colab and code this out and show you some neat and nifty applications of Python to actually see how heat diffuses through the bar and looking at when it approaches a steady state.
Okay, jumping over into Google Colab, we're actually going to sort of depict the relationship between temperature and time for our established bar with an initial condition of 300 degrees Kelvin and one end being 400 degrees Kelvin while the other's at 350 degrees Kelvin. We're going to model the finite differencing equation showing how heat diffuses across those little segments, which we will define in Google Colab. To start with, I'm going to import a lot of stuff that will be useful. First of being NumPy to do some of our array operations. Also going to import Plotly because we want to plot some things, and then from Plotly.subplots import make subplots. Yeah, so we're gonna establish some subplots. Spelled things wrong. I usually spell things wrong, so there we go. Hopefully that works. And then the first thing we want to actually establish, and we want to declare some variables before actually diving into the equation and plotting its relationship to time, is we want to actually define how many segments we're going to divide this bar up into. And for this, I'm going to choose 1,000 segments. So divisions in bar, and this is important for the finite differencing equation. The whole reason it works is that we're saying, hey, we have these little slivers within the bar, and within that sliver, it's all the same temperature, but the temperatures can vary to the left and to the right of those little blocks. I'm going to actually call them blocks going forward. Another thing we also want to declare is the number of time, or the amount of time. We just want to let this bar sit. Steps. So we're going to say 10,000 time intervals, and you can actually determine units on time from your R value, and if you remember, the R value is your heat diffusivity times time steps divided by your steps in position squared. So you can derive units from that R value because you know the units for heat diffusivity, time step, or your change in position, whatever you want to determine. And then next, we're actually going to code in the simulated bar and its initial position using a NumPy function of full, and it'll have 1,000 values, and we all want those initial values to be 300. I'm going to make it a floating point number because some of the changes will be less than a whole integer, and we want to be as accurate as possible. Next, I'm going to declare the initial conditions of the bar being at 350 degrees Kelvin. So that we'll call this the left side, and then we're actually going to call the right side and write that its temperature is 400 degrees. And remember, these will not change as time progresses. So when we go through and actually code the finite differencing equation, we're going to emit those values. Another thing, just a little nuance to arrays and indices in Python is that it always starts at 0. So the first block has an index of 0, and it'll go all the way up to 1 minus the total number of blocks we have. And another way you can reference those is by actually calling negative numbers to work backwards from 0. So this -1 is the absolute last position in the block. And the reason I'm doing this, as opposed to just writing in 1,000, because we know there's 1,000, is first I would call it 900 or 999, because again, it's 1 minus the number of positions you have. And also, it gives us the flexibility to work backwards and change the number of divisions we have in that block. So if we wanted to increase or decrease it, we don't have to go through and hunt for these -1 values and change them. Next, since we're going to be creating a graph, I'm going to create an axis, and I'll be doing this by just creating something simple of using a numpy function to create an array that goes from 0 to the total number of values in that array. In this case, we're going to have 1,000. Next, let's go ahead and actually declare our subplot, subplots and rows. We're just going to have one graph. Columns, we're just going to have one, making it real simple. And for OCD's sake, by fixing that. Next, we're going to actually graph our initial condition, and we're going to add scatter, because this is a scatter plot. We have a data point for each position in the bar. Our x-axis is going to be what we defined it to be. Our y-axis is going to be our initial temperature position, and then we'll want to actually go ahead and connect those dots in a line, and let's call this initial. Nice. Okay, then we actually want to go ahead and write a for loop describing our change in time as we progress through time, and we'll do all the way up to total number of time steps defined. Next, we actually want to go ahead and write the finite differencing equation we derived earlier. And remember, we're only going to be updating the middle values, so that's why I'm doing 1 all the way up to -1. On the left-hand side, it is inclusive, so it includes, this is the second block, and on the right-hand side, it's not inclusive, so it doesn't include the end, the very end. And if you remember, that temperature of that block depends on the previous temperature, which is this term right here, times that R value, which was the heat diffusivity times the time step divided by your change of position to the squared. And it's also going to depend on the position to the left of it and right of it. In this case, we're writing the right. And it'll depend on 2 times the change in, not change, this and the previous temperature. I keep wanting to actually go ahead and write -1 colon 1, but that's incorrect. You always have to do the smallest indice first, going to largest, and even though the -1 is a smaller integer, it's not arranged that way with indices. So we're going to go ahead and do it all the way up to the right-handmost side. So before we actually go ahead and continue further, just take a look at this equation here, and we can see that your temperature of a block 1 step in the future depends on your current temperature, this value here, and then it also depends on the temperature of the blocks to the left and to the right of it. So this is how heat will actually diffuse, and how much of that heat diffuses depends on this R value and directly your heat diffusivity. So next, we're going to go ahead and do something nifty for actually plotting. And if your integer, we're going to use the modulo operation, is divisible by 1,000 and is equal to 0. This is basically saying for every 1,000th time step, we're going to want to create a plot for that. And I'll go ahead and add a scatter x. We're going to have the same x-axis. For our y-axis, we're going to have our updated t position, or not t position, our updated temperature. And then we're going to have, it's also going to connect the dots. We're not going to have the same title. For this, we actually want to call it just whatever position it is in time. And then, at the very least, at the very last, we'll do fig show. And hopefully this works. And yeah, so fig show, it should show us 10 plots. Really quickly, we see here, there, it doesn't go all the way up to 10,000, which is what the number of time steps we will have. This is because of the nuance of how range loops work in Python, and they only they're not inclusive, so they don't include the term they go up to. So we're going to include that 1 to go all the way up. And you can see here, as time progresses, heat diffuses across the bar, and it's taking quite a bit of time actually. So we'll go ahead and increase the total amount of time we let this bar sit for, essentially. And whenever you're changing previous variables, you always need to run that block of code again. I'll run that again, and I'm just amplifying everything by a factor of 10, so you'll still have 10 plots. And here we can see we counted the 100,000th value. This is because we actually included that +1 there. Still making some more progress, but nowhere near as linear. Another thing you could do to change how fast heat diffuses across this bar is also changing this R value. And for this material, it's unlikely that you're ever going to be able to change the heat diffusivity of material, but you are able to change the time step or your change in position. So I'm going to change the R value to 0.3, rerun everything, and hopefully we should see heat diffuse across the bar at a faster rate. And yeah, it's looking better. It's lifting off the axis a little bit more. I'll go ahead and increase it further to 0.5. And yeah, okay, it's looking good. It's progressing a little bit more. So let's go ahead and actually increase the time this time. No pun intended. But always remember, update the blocks after you change a variable or change anything within that block. And this will probably, this is also another reason why we're using Google Colab, is imagine doing this by hand. It'd be absolutely insane, and the number of computations alone would probably drive me crazy, honestly. But there's probably some people out there that could really get into the weeds of everything and enjoy it. And here we actually see we do reach a steady state, and this can be signified by there is no change in temperature based on time at any given position. The only change in temperature is actually based on position, so along that bar, it's a straight line. So that signifies steady state. So let's see if we can try and reach it at a faster rate, rather than taking, I think that was 1,000,000 time steps. I'll actually increase this R value to 0.51, and saw a blip of something, a little foreshadowing for, yeah, this doesn't look like what we should be looking at. Common sense tells us that you probably can't get that bar up to a temperature of 10 to the 167th Kelvin. That's pretty extreme, and just the way it oscillates, it looks pretty unstable. But maybe it's just a blip. Let's try and back off a little bit. Maybe do a larger time stamp, and maybe we'll see something different. Maybe that was just a fluke. But this actually is going to be a good segue into the next video, covering the instability around using finite differencing. And wow, yeah, so that's ugly. That's nothing that we wanted to actually see. Can't even really tell what's going on there. So I'm going to decrease time step by more. Go back to, I think, so that's 50,000, and then do plot every 1,000th interval. Yeah, so again, we see this sort of oscillation, and it's obviously not reliable because you're not going to have these values. And this is actually approaching one of the next limitations of using finite differencing. So, in the beginning we stated those assumptions which sort of limit our range of scope and use of finite differencing. Well, there's actually another limitation which we will explore further in the next video around this instability when you cross this threshold of an R value greater than 0.5. So that's it for this video. I appreciate you watching. Hopefully you learned something, and it's been a pleasure. So thank you.